Hey there, awesome physics students. Let's talk about power. Power is defined as the rate at which energy is transformed. So it's the increase or decrease in energy divided by the time interval over which that occurs. You'll find other definitions in terms of work or something like that, but work is an energy transformation too, so this definition is more broad and covers most of the scenarios that you're going to encounter. In everyday language, we often talk about power in terms of cars, like my car has a lot of power or my car doesn't have very much power. Well, if you think about what a car does, you press on the accelerator and the car increases its kinetic energy. The kinetic energy it's gained is the energy that's transformed. And if that kinetic energy gain occurs over a very small time interval, that is delta t is very small, you're going to divide by that small number, you're going to get a very large output power. If, on the other hand, your car doesn't accelerate very quickly, the time interval is going to be big, and so you're going to divide by that bigger number. The output power is going to be a lot smaller. So this actually correlates really well with how we talk about power in everyday life, at least in terms of our cars. Now, if we look at this, energy has units of joules and time has units of seconds. So this is a joule per second. Or we also use the term or the unit watt, which is a joule per second. So you probably encountered watts, at least in terms of everyday appliances. And that is the same watt that we're talking about here. Let's do an example problem here. So imagine that you have a cyclist who is going to climb up a steep hill. And while they're doing that, they can put a mechanical output power of 200 watts. So just to say, this is the mechanical power that they are outputting, not necessarily the power they're consuming internally. Let's say they have a mass of 68 kilograms and they're climbing a hill. And the hill, we don't know how high they've climbed, but we know that they can climb this hill in about 30 minutes, which is 1800 seconds. So the question is, what's the altitude gain that they could incur over that 30-minute time interval? Well, first let's try and find the amount of energy that is transformed. So if we know the power and we want to find the energy transformed over time, we can rearrange this to find the energy transformed. And that's just going to be, if we multiply both sides by the time interval, that's going to be the power times the time interval. Well, we know the output power is 200 watts and we know the time interval, so we can actually compute this. So the energy transformed is going to be the 200 watts times the 1800 seconds. And we need to use the seconds because a watt is a joule per second. And so when we compute that number, we actually get 360,000 joules, or 360 kilojoules. Okay, now how can we connect that to the height? Well, think about what's the energy that's transformed here. They're converting their internal chemical energy in their body into gravitational potential energy. And while they're doing this, we're assuming that they travel this hill at constant speed, which is a very reasonable assumption in this case. So really they're converting this, and the mechanical power, the mechanical energy they're gaining is just gravitational potential energy. So that's just mgh. So we're saying that the 360,000 joules is mgh. And so we need to find the h in that mgh. Well, we know their mass, so we can just divide both sides by the mass and the gravitational constant g. And that will cancel those. And so what I need to do is, so that tells me that the height is equal to 360,000 joules divided by the mass, which is 68 kilograms, times the gravitational constant, 9.8 newtons per kilogram. And when I compute that number, I get about 540 meters, which if I convert this into more everyday familiar terms, this is about 1,800 feet. So they've actually gained a fair amount of altitude during this 30-minute exercise period. Okay, the last thing I want to do is think about, if I were to take this 360,000 joules and convert it into food calories, how many food calories would that actually represent? So we take the 360,000 joules and we multiply it by the conversion of 1 kilocalorie, or 1 capital C food calorie, is equal to 4,184 joules. And when so I'm multiplying by 1 here because 1 calorie is, these amount of energy units are equal to each other. So when I compute that, I get about 86 food calories, or 86 kilocalories. Now, if I compare that to the amount of energy, food energy, in like a bagel or a candy bar, that's going to be about 200 to 300 food calories. So this isn't even this isn't even half of a candy bar, half of a bagel. Now, that is assuming that the person can convert all of their internal chemical energy from the food that they eat. 100% of that is going into gravitational potential energy, mechanical power out. That's not true. So that part, actually, if you think about what's going on here, their internal chemical energy is being converted into gravitational potential energy, but a large portion of it is also going to increasing their internal body temperature, which they will try to shed by sweating and things like that. So a lot of that is going into thermal energy. In fact, most of it, we'll find, is going into thermal energy. So you can't necessarily think of these as candy bars directly, because it doesn't correlate quite that way. And the reason is because we used mechanical power output and we weren't thinking about the input. Okay, so hopefully this gives you an idea of how to use power and how to connect that with some of the food calories, even if it's not exactly an honest comparison. All right.